Hello friends, welcome to this YouTube channel. Today we are going to solve one numerical problem on three-phase medium length transmission line. By solving this problem, we shall learn how to determine percentage voltage regulation and efficiency of transmission of a three-phase medium length transmission line using its nominal pi equivalent circuit when values of transmission line parameters and load details are given. A three-phase 50 Hz 100 km long transmission line delivers a load of 20,000 kilowatts at 110 kV at 0.9 power factor lagging. The copper conductors of the line are 1.2 cm in diameter and are spaced equilaterally so that the distance between them is 2 meters. Using nominal pi method, we have to determine the sending end voltage, current and its power factor. We also have to compute the percentage voltage regulation and the efficiency of transmission. Let us first write down the given data. Power delivered to the load PL equals to 20,000 kilowatts. Line to line receiving end voltage VR line equals to 110 kilovolts, that is equal to 110 into 10 to the power 3 volts. For star connected system, receiving end voltage per phase VR equals to VR line divided by root 3, that is equal to 110 into 10 to the power 3 divided by root 3, that gives us 63,508.53 volt. Given load power factor cos phi L equals to 0.9 lagging. Let us now calculate power factor angle. Phi L equals to cos inverse 0.9, that is equal to 25.842 degree. We know that power delivered to the load PL equals to root 3 times VR line into IL cos of phi L. Therefore, load current IL equals to PL divided by root 3 times VR line into cos phi L. Using values we get 20,000 divided by root 3 into 110 into 0.9, that is equal to 116.6364 ampere. Load current may be written in polar form as IL equals to IL at an angle minus phi L, that is equal to 116.6364 ampere at an angle minus 25.842 degree. This may be written in Cartesian form as 104.973 minus J times 50.8406 ampere. Given length of the transmission line D equals to 100 kilometers, that is equal to 100 into 10 to the power 5 centimeters. Diameter of the conductor D1 equals to 1.2 centimeter. Equilateral spacing between conductors D2 equals to 2 meters, that is equal to 200 centimeters. Let us now calculate radius of the conductor. R equals to D1 by 2, that is equal to 1.2 divided by 2, that gives us 0.6 centimeter. Expression for inductance per kilometer per phase L1 equals to 0.05 plus 0.2 into log of D2 by R millihenry. Using values we get 0.05 plus 0.2 into log of 200 by 0.6 millihenry, that gives us 1.21183 millihenry. Now we shall calculate inductance per phase. L equals to L1 into D. Using values we get 1.21183 into 100, that gives us 121.183 millihenry or 0.121183 Henry. Expression for capacitance per kilometer per phase, C1 equals to 1 upon 18 into log of d2 by r microfarad. Using values we get 1 upon 18 into log of 200 upon 0.6 microfarad, that is equal to 0.0095635 microfarad. Let us now calculate capacitance per phase. C equals to C1 into D. Using values we get 0.0095635 into 100, that is equal to 0.95635 microfarad or 0.95635 into 10 to the power minus 6 farad. Let us calculate cross-sectional area of the conductor. A equals to pi r square, that is equal to pi into 0.6 square, that gives us 0.36 times pi square centimeter. Resistance per phase, R equals to rho into D by A. We know that resistivity of copper, rho equals to 1.73 into 10 to the power minus 6 ohm centimeter. Therefore, R equals to 1.73 into 10 to the power minus 6 into 100 into 10 to the power 5 divided by 0.36 times pi, that gives us 15.3 ohm. We have computed inductance per phase, L equals to 0.121183 Henry, and capacitance per phase, C equals to 0.95635 into 10 to the power minus 6 farad. Let us now calculate inductive reactance per phase. XL equals to 2 pi f into L. Given supply frequency f equals to 50 Hz. Therefore, XL equals to 2 pi into 50 into 0.121183, that gives us 38.0707 ohm. Capacitive susceptance per phase, DC equals to 2 pi f into C. Using values we get 2 pi into 50 into 0.95635 into 10 to the power minus 6, that is equal to 3 into 10 to the power minus 4 mho. Series impedance per phase of the transmission line, Z equals to R plus JXL, that is equal to 15.3 plus J times 38.0707 ohm. This may be written in polar form as 41.03 ohm at an angle 68.1 degree. We have computed transmission line series impedance per phase, Z equals to 41.03 ohm at an angle 68.1 degree, and capacitive susceptance per phase, BC equals to 3 into 10 to the power minus 4 mho. Now we shall calculate capacitor charging current at the receiving end. ICR equals to VR into half of J times BC. Taking receiving end voltage per phase as reference, we can write VR equals to 63,508.53 volt at an angle 0 degree. Therefore, ICR equals to 63,508.53 at an angle 0 degree into half of 3 into 10 to the power minus 4 at an angle 90 degree. That gives us 9.5263 ampere at an angle 90 degree. This may be written in Cartesian form as 0 plus j times 9.5263 ampere. Now we shall calculate current flowing through the series impedance. I equals to IL plus ICR. We have computed load current IL equals to 104.973 minus J times 50.8406 ampere. Using values we get I equals to 104.973 minus J times 41.3143 ampere. This may be written in polar form as 112.81 ampere at an angle minus 21.483 degree. Now we shall calculate sending end voltage per phase. Vs equals to Vr plus I into Z. Using values we get 63,508.53 at an angle 0 degree plus 112.81 at an angle minus 21.483 degree into 41.03 at an angle 68.1 degree. That gives us 66,687.78 plus J times 3,364 volt. This may be written in polar form as 66,772.573 volt at an angle 2.8878 degree. Now we shall calculate capacitor charging current at the sending end. ICS equals to Vs into half of J times Vc. Using values we get 66,772.573 at an angle 2.8878 degree into half of 3 into 10 to the power minus 4 at an angle 90 degree. That gives us 10.016 ampere at an angle 92.8878 degree. This may be written in Cartesian form as minus 0.5046 plus J times 10 ampere. Now we shall determine sending end current. Is equals to ICS plus I. Using values we get 104.4684 minus J times 31.3143 ampere. This may be written in polar form as 109 ampere at an angle minus 16.686 degree. We have obtained sending end voltage per phase. Vs equals to Vs at an angle delta equals to 66,772.573 volt at an angle 2.8878 degree, and sending end current Is equals to Is at an angle minus 51 equals to 109 ampere at an angle minus 16.686 degree. For star connected system, line to line sending end voltage Vs line equals to root 3 times Vs, that is equal to root 3 into 66,772.573, which is approximately equal to 115.65 into 10 to the power 3 volt or 115.65 kilovolt. Phase difference between Vs and Is, phi s equals to delta plus phi 1. Using values we get 2.8878 degree plus 16.686 degree, that gives us 19.5738 degree. Now we shall calculate sending end power factor. Cos phi s equals to cos of 19.5738 degree, that is equal to 0.9422 lagging. Now we shall compute sending end input power. Ps equals to 3 times Vs into Is cos phi s. Using values we get 3 into 66,772.573 into 109 into 0.9422, that gives us 20,572.6 into 10 to the power 3 watt, or 20,572.6 kilowatt. Now we shall calculate efficiency of transmission. Eta T equals to PL divided by PS. Given power delivered to the load, PL equals to 20,000 kilowatts. Therefore, eta T equals to 20,000 divided by 20,572.6. That gives us 0.9722 per unit, or 97.22%. Now we shall remove the load from the receiving end and calculate capacitor charging current at the receiving end on no load. ICRO equals to Vs divided by Z minus 2 into JXC. We have obtained sending end voltage per phase. Vs equals to 66,772.573 volt at an angle 2.8878 degree. Per phase series impedance of the transmission line, Z equals to 15.3 plus J times 38.0707 ohm, and capacitive susceptance per phase, Bc equals to 3 into 10 to the power minus 4 mho. Let us now calculate capacitive reactance per phase. Xc equals to 1 upon Bc, that is equal to 1 upon 3 into 10 to the power minus 4. That gives us 3333.3333 ohm. Now we shall determine Z minus 2 into JXC. Using values we get 15.3 minus J times 6628.596 ohm. This may be written in polar form as 6628.6 ohm at an angle minus 89.8678 degree. Using values we get ICRO equals to 66,772.573 at an angle 2.8878 degree divided by 6628.6 at an angle minus 89.8678 degree. That gives us 10.0734 ampere at an angle 92.7556 degree. We have obtained capacitive reactance per phase. Xc equals to 3333.3333 ohm, and capacitor charging current at the receiving end on no load, ICRO equals to 10.0734 ampere at an angle 92.7556 degree. Now we shall calculate receiving a voltage per phase on no load. VRO equals to ICRO into minus of 2 times JXC. Using values we get 10.0734 at an angle 92.7556 degree into 6600 66.6666 at an angle minus 90 degree. That gives us 67,156 volts at an angle 2.7556 degree. Now we shall calculate voltage regulation, that is equal to VRO minus VR divided by VR. We have computed receiving end voltage per phase on load VR equals to 63,508.53 volt. Therefore, voltage regulation equals to 67,156 minus 63,508.53 divided by 63,508.53. That gives us 0.0574 per unit or 5.74%. So today we have solved one numerical problem on three-phase medium length transmission line. By solving this problem, we have learned how to compute voltage regulation and efficiency of transmission of a three-phase medium length transmission line using its nominal pi equivalent circuit when load details and values of transmission line parameters are given. Hope this lecture has been useful for you. If you have any suggestion or question, please drop it in the comment section below. If you have liked this video, give it a thumbs up and share it with your friends. Thank you.